Hello, everyone. First of all, I'm very grateful for the invitation of the HDB. The topic I share today is the art of the Windows kernel first. Okay, let's begin. Okay, this is my agenda, my self introduction, something about the Windows kernels first, the framework, architecture, the fast results about and the build SDKs, the next generation fast system, and overflow bug to export, and the conclusion and the further work. As last is question and answer. So, as first, please allow me to introduce myself. I'm from Kitchen General Lab. I'm a researcher. I'm focused on Windows kernel, especially the local priority execution. This is my Tinder, my interest. My interest is reverse engine vulnerability research and malware analysis. Okay, before we start, we must know what are our goals. Our goal is very simple. Our goal is to find many kernel vulnerabilities. Yes. And what do we aim? Let me take a look at the main target. In the last year, my main target is the Windows object, just like the GDI object, just like the DC, BRAM, palette, RGN, pin, brush, and path, and some user object, just like the desktop, menu, icon, hook, accelerator, table or window, or the other system objects. Actually, we aimed any possible object on the Windows. There's the target mode. Yeah. This is something about the fuzzing. The fuzzing is the automatic software testing technology. We need the immediate unexpected or random data used as the input. We need a monitor to monitor the target program from the crashes. And the most important thing is how to generate the random new input and put the random input feedbackly or manually. Okay. This is a simple framework architecture. At first, we need a fuzzing script. My fuzzing framework is written by Python, not written in C. We need to write Python. We need to write Python, and we need the test cases, and we need a fuzzing server and the dump collector, and our framework architecture's goal is easily reproducible. Yeah, this is the framework. At first, you must need a security researcher. You must need a researcher and several PC machines, and a monitor to collect the bugs to the server. And the register is responsible for writing the scripts, so for the fuzzing scripts. The script will generate many fuzz cases and push them into the every fuzz machine, and the monitor will collect the bug and into our log server. Of course, we need to write down some fuzz logs to help us improve our fuzz. Okay, here is how the kernel framework works. When the system starts, it will run a monitor to prevent the abnormal situation in fuzz system and restart the system, particularly every 5 minutes. And the system will reboot. It will update the latest fuzz script. Fuzz range, and then the system will generate the policy template and the test case, and the fuzz machine will run these fuzz scripts. And if we find a system crash, the fuzz framework will upload the log and the crash dump, and it will save the test script. Yeah. Here is how to find the target functions. If we want to fuzz, we must know the target functions. I find a very simple way to find the target functions. You can use the tool. It's called the WinDBG. You can use the WinDBG. You can use the command X, and you can find many functions. You can choose some of them interest you. Here is the functions. Here the functions interest me. The left functions is for generate various objects. That's like the first one is for create DC. The next one is for create a bitmap, and the next is the palette, argin, and the color and the pen. You can generate many objects. The middle one functions is for the fuzz operates. When you want to fuzz object, you shall collect all the functions associated with the target objects. The third one in the right is the functions for destroy or delete. For destroy object. So in a fuzz framework, you should create object first and collect the target function associated with the target objects, and the function of destroying the objects, and the fuzz framework will help you make all the functions in a array in Python. In array, you can call any functions of them, and randomly and repeatedly. If you're lucky enough, you will run the fuzz framework for a week or month. You will find the system is done, is born, the system is crashed. If you're not lucky enough, you should add the functions until you can find the system crash. Okay, this is the fuzz script, very simple. So you can, the first is the DC, the second is surface, the third one is RGN. So when you want to fuzz DC, at first you show to collect all the operations associated with the DC object, and save them to array, a Python array, and just like the other objects. So you can call them randomly and pick any function from the array. Then here is the fuzz result summarize about 10 to 20 crashes in a year, in the last year, but a lot of non-reproducible crashes, and some of non-difference pointers, and the next is the crash tab. I found the session vivid32 and the key mode is represented not handle. The session will have vivid special and the page fault. Here is effective crash summarize. I found 3 to 4 UF and 2 to 3 integer overflow, and 2 range condition, and none difference. Here is a POC for series 2018 and 8166. You can see the POC crashed the added function, GDI function, and the POC is reproduced by the Python object. And here is the fuzz result and the build SD cases. You can see that this is class demos when I fuzz the windows and generate some crashes. Okay, in the following section, I will introduce the next generation fuzz system. The new fuzz system is made of the CPU P-trace and the FL, the Kernel, and with my traditional fuzz and some method with the S2E. S2E is for symbolic execution. Okay. Here is the FL kernel fuzz framework. At first, we need Intel CPU. We need a CPU support the P-trace feature, and we need a software to decode the CPU's stream and have the fuzz to find more branches. At first, the CPU will generate the data, and the data will set to the software decoder, and the decoder will decode the CPU data, and when the decoding finished, the software, the inter-PT software decoder will tell us we get how many branches we get. And here is the program, the FL kernel fuzz framework. At first is in the CPU, and the next level is the KVM P-trace. We need a KVM. The second one is the QMU P-trace. We need a QMU, and we change the QMU. And the next one is a filter. We need a filter to find the block branches, provide data for the FL, and to create the bitmap. The last one is the key FL. The FL will record the symbol according to the feedback when veneration symbol. This is the FL kernel fuzz framework. This is the FL kernel fuzz test result. And find file vulnerabilities. And we need the memory for 4 GB, and we need a CPU support P-trace. Here is the demo. You can see that. The left is the kernel FL. The right is traditional Windows kernel fuzz. We combine them. Here is the advantage and the disadvantage of the FL kernel fuzz. The advantage is we can cover more code and automatic veneration, and the KVL multi-platform support. We can fuzz Linux kernel, Mac OS. Mac OS will support in the future. The CPU, the third advantage is the CPU. CPU hardware is very efficient. This advantage is encounter a single irregular integer number is proved to infinite loop, results in low fuzz efficiency and low path coverage. Let me show a symbol. This is the biggest program in actual fuzzing. When you meet a program or when you meet the code just like this, if you want to reach the target vulnerability code, how do you can do it? Not manually. Auto reach the vulnerability code. This is the biggest program. So the biggest program in actual fuzzing is when if you process the code branches, the input is random muted. If the I does as input, if you random run an integer, you will not reach the target vulnerability code. You will never reach it. It will spend many times to reach that vulnerable code. You can't wait it. So how to make up the FL shortcomings? We looking for the related coverage technology explosion. We found the existing symbol execution technologies. We researched the Anger, the S2E, and the WinFL. And finally, we chose the S2E. Here is how to solve the special path with the symbolic execution. If we meet the particular code, the S2E will calculate the path conditions for us. That's like the filter. The S2E will calculate a value, help us to reach the three paths. The path 1, you can the alpha is 1, the beta is 1. Path 2, alpha 1, beta is 6, and you can reach any path in your program. So, how to improve the feedback fast? In my research, I combine two technologies. I combine the FL and the S2E, and we can get more complete path coverage. and how to connect the S2E and the KFL, and the import to FL is a string, and the import to S2E is also a string. So we can use the same string as the seed at the same time. If we can find more paths with the KFL, and we can try the S2E. If the S2E doesn't work, we can try the AFL to help us. Here is the combined result. We can find for a small scale code, it's easily to find all the coverage paths, and for complex operating system, the S2E also have many problems. In the next part, I will sell POC details. Sell POC. This is a POC 2019 and 623. You can see the POC code. Here's a piece of code of POC. You can see that at first we need to create two cursor, and we need to create them with the different size, and the cursor one will be set link x 300 and link x 2D8, and the second one is link x to 300 and link x to D0. Then we will call the ND user set cursor contact, and this function will copy the cursor's tools config to the cursor file, and at last when we update the cursor, the miracle happened. Here's details about the POC. What will happen when the POC run? When the POC runs, the system will change the cursor's object some value. The value is for a size, for a memory size. But the system will not apply for enough memory for the new cursor. The system changed the cursor size, but the system didn't apply for enough memory. Here are the details. You can see the bug is there. It will add the bottom of the rect and add the old one with the new rect bottom. And here we can see the link 005AA. You can see that 005AA is added by link x to DA and the link x to D to D0. From here you can see it added the cursor's y. You can add the cursor's to point y and the cursor's file point y. It added some. So you can see is stored in the memory. And when we run next function, what will happen? They will call the ing copy backs. It will call this function. And as last, what will happen when we run the whole POC? You can see the system crashed. You can see that the memory corrupt. Here's the details. The memory copy details. You can see the target size is 5AA. And what will happen when the cursor update? Actually, we already get a heap overflow. We already get overflow. Here is the details about what will be happen when the cursor update. We get a memory overflow. The next part is some details about the export. As you know, we get integral flow. If you just want a crash, you can finish your work. If you get a export and many works you need to do. You need to do many works just like this. The export process just like this. You can put the slide just like this. You can just like the memory, the picture just like the system's memory. You can you shall put all the objects regularly and put them together and make it stable. You need to make it stable. And how to make arbitrary read and write? As we get integral overflow, we need we need convert integral flow to use R3. So we choose the menu object, and we put the menu object behind of the cursor object. When the overflow happened, it will write manual's clock. It will set the clock from 1 to 0. When the clock is set to 1, the manual is locked. You can't free lock the menu. And when you set the bit is the set bit to 0, the lock is unlocked. And now you can free a menu. So you can gain you use a free bug. So you can spray the data at the heap and gain a read and a write arbitrary read and write. Here is the export demo. when we did a lot of work, and finally we export the Windows kernel. Here is a demo. You can see it. As you can see, we export from a normal user, and it's kept to the system. We export the system. We can add any user we want. We can add a user. So the next part is the fuzzing challenge. In the next part, I will share the challenge I faced during the fuzz. On the Windows 10 7009, the Microsoft introduced a tab isolation mechanism to prevent the use of free bugs. In my experience, the user-free bug of the GDI object is almost over after the tab isolation. And this is something about the GDI object tab isolation. I will show the normal GDI object chain and the object memory layout change, and how it makes the fuzz more harder. And you can see the picture. Here is the GDI object attack chain, and there is normal way of using a user-free to exploit. If we got a UEF issue, we can spray the object to the heap and get the arbitrary address read right. And as you can see, now we can't get arbitrary read right because the tab isolation. Here is how the tab isolation works. Before the tab isolation, we can spray the data in the pool. We can control the object's header, and we can control the object's header part and the data part. If you get user free, you can spray in the heap. You can control the service header and the service data. Here's the after tab isolation, the service object will divide into two parts. The header will alloc in kernel isolation session map view, and the data will alloc to heap. When we create a service or free service, you can see that the operation is worked as at the session view. Here the details about the service header create and free. We can spray to the isolation heap. As you can see, if you free the service tool, that will left a free slot on the view 1, and the free slot will be filled with next service object. So we can't control the sprayed laser. So we can't. So the URF can't be exported by this way. Here are the details about the isolation. At first, you can find the base G pointer type isolation is a pointer, and you will find the C type isolation struct, and you will find the double link, and on the double link you will find the view contain the GDB object headers. You can find the headers. And this picture shows the service data log and free. The service data is logged on the session pool, and we only can spray to the data part. We can control the data part, but the header is locked on the map view. Okay, the header. The header is locked on the view. We can't spray to this view. So we can't control object. We can't control the object's length. We need to control object's length or size. Something you can get a system reader, system arbitrary read or write. Sorry. Here is the details about the service type isolation. You can see that in the service header, the data and the header is no longer together. There is a pointer on the service header, and you can find the data band pointer, but they never together. Here the GDI object for pass is also applied with the type isolation. As we can see, the object is created by C-type isolation. Here is the palette, also implemented with the type isolation. Okay, now let's make a summarize. In my last year, my first focus my first focus on Windows object, and we get some vulnerabilities include user free and integer overflow, and we write export. In the future, the user free is few, and we will focus more objects. We will fuzz the other system objects, and in the future, I will update my fuzz architecture and update the component and algorithm, and I will do more export method research. Okay, thank you everyone. Thank you.